Using all of the letters in the word Columbia, determine the number of possible arrangements if. Okay, so we're arranging the letters in the word Columbia, and then we're going to do a bunch of different scenarios. So the first one is if there's no restrictions. Okay, so if there's no restrictions, what are some things that you want to look at before you actually start figuring out the number? Yeah. Yeah, how many letters are in the word, right? So there are 4, 5, 6, 7, 8 letters. Okay, and there's one other thing that I would check. Yeah?
Would you check to see if two of the letters are the same?
Exactly, yeah. So check for identical letters, okay? In this case, they are all different. They're all distinguishable, okay? So if we're arranging all the letters and there's no restrictions, then we can have our 8 spaces. Okay, and we have 8 options for the first one. Times 7, times 6, times 5, times 4, times 3, times 2, times 1. Or 8 factorial, right? So in the sort of most basic case where there's no restrictions, that's where we see these factorials come up a lot. 8 factorial ways of arranging those letters, okay? What about if the first letter must be an L? Okay, the first letter must be an L. Which space would you deal with first? The first space, yeah. Deal with the space where there are restrictions, right? So if this has to be an L, how many options do we have for the first space? 1. Has to be an L. Okay, what about the second one? Yeah, so 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? The last 2 letters must be vowels. Okay, the last 2 letters must be vowels. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And the restrictions are in the last 2 letters. Vowel and vowel. Okay? So if we're dealing with those last 2 letters first, how many options do we have, let's say, for this one? 4. There's 4 vowels in this word. So it's O, U, I, and A. Right? Okay, so once we place that one, how many options do we have for the last letter? 3. Yeah. Okay, so we've done the restrictions. Now we can go back to the beginning and think, okay, how many letters do we have left that need to be placed? 6, because we've used 2 up, right? So once you use up 2 here, there's still going to be 2 vowels that remain, and those will go back into think of it as like a Scrabble bag with the 4 consonants. And now we have 6, 5, 4, 3, 2, 1, right? So in this space, there are 6 letters left after placing the last 2. Okay. The letters O and M must be adjacent. Yes?
Just a question for C. What would that be in factorial?
This one.
A is 8 factorial. What would that be?
Yeah, so you could write this as like 6 factorial times 12, for example, but you can't write this answer as a single factorial. Yeah. Yep.
Could B be written as 7 factorial?
Yes. B could be written as 7 factorial. Yeah. Okay. It's actually a good question because I've seen certainly on the 30-2 diploma, you'll see these types of questions, and some of the options for multiple choice will be given as factorials rather than just the numerical value. So yeah, you could see this as 7 factorial. This could be 12 times 6 factorial. Yeah, you could see something like that. You can also, like if you're unsure, just use your calculator to evaluate all of the different options and see which one matches up with your answer. Okay, what if the letters O and M have to be together? What if they have to be together? Yes.
You have to count for like every place that they can be.
Yeah, they could go, so that's the thing, right? They have to be together, but they can be anywhere on the line, in the line. Okay. So, I need some people, 2 people who like are willing to come up here and hold hands. Will you guys do it? Okay, come on up. Okay. So Tessa and Dominique have to be together. There's always some people in this class, in a class, who have to be together. They are joined at the hip. They will not detach from one another. Okay? So we are going to consider them one object. They're only one object. However, do they have to be together in this orientation? No. Okay, so what's another way? There you go. Yeah, exactly. So that's how we're going to treat this type of question. We are going to treat O and M, okay, you guys can sit down, as a single object. Because they cannot be separated. Okay, so we don't have 8 objects anymore. We only have 7. Yeah. However, O and M can be arranged in 2 different ways. So you have to think, okay, now it's almost like saying we have 7 objects. Okay? But you have to multiply that by like the 2 ways that O and M can be arranged. Yeah. So it's 7 factorial times, this is 2, but in general, if the group was bigger, it would be like 2 factorial, right? If we had a group of 3 letters that had to be together, well, now you only have 6 objects. You have the group plus the 5 other letters. So that would be 6 factorial, and then multiply it by the number of ways the group can be arranged, 3 times 2 times 1. Okay? This type of question is called a group within a group question. So it's a group within a group. And in general, what you want to do is treat the group as a single object. Right? So that was, if the group is a single object, in this case, there are only 7 objects now. So you do the 7 factorial to see how many different ways can you arrange that group plus the 6 other letters, but then you also have to multiply it by the number of ways that you could arrange the objects in the group. Okay? Okay, so if I were to change this, let's say I said in this same word, all of the vowels have to be together. Let's add an extra one. This is F. Number of arrangements if all vowels must be together. Okay? So if all the vowels have to be together, we have the word Columbia, right? So the objects that we now have to arrange are the vowels, O, U, I, A. That's one group, because they have to be stuck together, plus C, L, M, B. Okay, so we now have 5 objects instead of 8. So there are 5 factorial arrangements, right? But then we also have to consider how many ways can we arrange the group, right? The group arrangements would be 4 factorial because there are 4 letters in that group. And so the total arrangements would be 5 factorial times 4 factorial. Yeah. Does that make sense? Okay. So let's get back to this one over here. Okay? And actually, I want to get a value for A and a value for D. So let's see, what is 8 factorial and what is 7 factorial times 2? 8 factorial is 10,080?
Times 7 factorial.
Oh, this is 10,080?
Yeah.
Okay, so this guy is 10,080, like that?
Yeah.
Okay, what about A? How many was this one? 8 fact? 40,320. Okay, so the last question is really hard unless you can kind of think outside the box a little bit, okay? So the last question is, how many arrangements of the letters in the word Columbia if O and M are not together? How many ways could we arrange them if they are not together? Yes. Divide instead of multiply? You're kind of thinking along the right lines, yes? Yeah, exactly. If you think about it, the total arrangements has to be the number of ways they're together plus the number of ways they're not together. Right? The total arrangements will be arrangements together plus arrangements not together. Which means the number of arrangements not together would be the difference of the two. Okay, so it'll be 40,320 minus 10,080. And in fact, a lot of counting method problems and probability problems are calculated in this way because these are called complementary events, being together or not together, meaning that they are opposites of one another and they consist of if you add them all together, they consist of all possible things that could happen. And so, like, if you think about it, it's the same type of question as, okay, if there's a 30% chance that it's going to snow tomorrow, What's the chance it's not going to snow tomorrow? 70, exactly, because they have to add up to 100%, right? Same sort of idea, yeah. So I don't know what that is, but whatever it is, it's going to be 30,000 something. 30,160, I think? No? 200, what is it? 260. 60 or 40? 40, that's what I thought, okay. Right? This is the important thing. The classic, I know that we don't actually do probability in Math 30-1, which I think is actually a detriment to the course because in reality, probably half the time we do any sort of counting method question, it's within a probability question, right? What's the chance of this happening? We have to figure out how many ways could it happen, how many ways could it successfully, right? So the classic probability question is if there are 30 people in a room, what is the probability that at least two people have the same birthday? Okay. Now, calculating the probability of that happening is incredibly difficult to do if you start with that probability. Okay? But, and it's basically because there are so many possible cases that could happen. Calculating the probability that nobody has the same birthday is actually pretty easy. And so what we do is say, okay, well, let's say there's a 50% chance that nobody has the same birthday. Then there's a 50% chance that at least two people have the same birthday. Okay? So it's actually quite common to solve questions like this, where you figure out a difference between the total and the number of ways that something could happen to get the number of ways that it couldn't happen. Okay. Cases. Speaking of cases. Okay. When you are looking at a case situation, how many ways could you arrange this or that? Okay. There's a couple of words that you really want to look out for that indicate that you might be in a case situation. Okay. One of the words is or. Okay, but some other things that you could say is at least or at most. Right? Let's say I said to you, you want to order a pizza and you can have at most 2 toppings. How many ways can you do it? Well, if you have so many toppings, you don't have to get 2 toppings. If it's at most 2, you could get no toppings. You could get 1 topping or you could get 2 toppings. So that word at most indicates that you have to now consider cases, right? So look out for those. When you identify that you're in a case situation, you want to clearly sort of label the cases, figure out the number of arrangements for each case, and add them together. Okay, so we're going to look out for this. Identify the various cases. Determine the number of arrangements for each case. And then add all cases together. Okay, so we're actually starting out with quite a difficult question with cases. An easier question, maybe I'm going to add in an easier question because this one is quite hard. But an easier question, I'm going to add in another one, would be something like the pizza example. So let's say a pizza parlor has 5 different toppings. And we'll just assume that this is excluding cheese. Like you get sauce and cheese. That's it. Okay? So how many different pizzas could you order? If you can get at most 2 toppings. Okay? So, yeah, this is a case scenario because you don't have to get 2 toppings. You can get 0 or 1 or 2, right? So the 3 cases, 0 toppings. Case 2, 1 topping. And case 3, 2 toppings. Right? Now, if you're getting 0 toppings, how many ways can you do that? 1. Yeah, because you're just getting the sauce and the cheese, right? This would be if you're getting 1 topping. 5. There's 1 space, and there's 5 options, right? Here, getting 2 toppings, 5 times 4. Although, even this is a little ambiguous because, like, some people order double meat or, you know, double pepperoni or whatever. I don't know how that would work. Maybe it'd be 5 times 5. I think we need a little bit more information. But we'll assume for now that you're getting different toppings. How about that? Okay? So you would go 1 plus 5 plus 20. It'd be a total of 26 different pizzas. Okay? So let's now go back to this question. How many 4-digit odd numbers can you make using the digits 1 to 7 if the numbers must be less than 6,000 and no digits are repeated? So we're not allowed to repeat. We need an odd number, 4 digits, and it's got to be less than 6,000. Okay. So firstly, let's talk about, there's a couple restrictions here. Number 1, we've got to have an odd number. So if we got to have an odd number, where's that restriction going to lie? Every second number? The last digit, yeah. It's the last digit. So you're right, it would be every second number if we could use all the digits, but we're not allowed to use all the digits here. We're only allowed to use 1 through 7, right? So 1, 2, 3, 4, 5, 6, 7. There's actually more odd digits in our pool than non-odd digits, right? But if you have an odd digit, you know the number ends in an odd number. Okay, so because it's odd, it must end in 1, 3, 5, or 7. Okay? What's the other restriction that we have? It's got to be less than 6,000, yeah. So where's that restriction going to lie? The first digit, right. What could the first digit be? Yeah. So must start with 1, 2, 3, 4, or 5. It's got to start with a 1, 2, 3, 4, or 5. It's got to end in a 1, 3, 5, or 7. Okay? Now, why do you think that this is a case problem? Yeah. Can't be repeated. Okay, true. Yes. Can't be repeated. But why would this be a case scenario? It has to do with the two things that we've already written down. Yeah. Yeah. We have various cases. Yeah.
Because like in case one you can start with a one, in case two you can start with two.
Yes, okay. So we could literally divide it into 5 different cases, but there's actually only 2 cases. The reason why this is a case problem is because we have to deal with 2 restrictions, and there's overlap in what can go in those places, right? So let's say we deal with this guy first, and let's say that's a 3. Now we have to take a 3 out of here because it can't be reused. Okay, so you have to think, okay, where's the overlap? The overlap is in 1, 3, and 5, right? So let's say case 1, it starts with 1, 3, or 5, and case 2 starts with 2 or 4. Case 2, I should say. Starts with 2 or 4. Okay. Now, I actually think I want to start with case 2 because it's an easier case to think about. In case 2, if it starts with a 2 or 4, how many options do I have for the first digit? 2. This has to be a 2 or 4. And also, this digit has to be odd. And if I use a 2 or 4 up first, I have 4 different odd digits that I can put in here, right? So I can put in a 1, 3, 5, or 7. So this is 4. Okay, now there's 7 digits altogether. If I place the first and the last, I've used up 2 of them. So now when I go and put the next 2 in, there's 5 left, and then 4 left. Okay. Now the other case is that I'm using numbers from this pool for both the first and the last digit. Right? So if I start with a 1, 3, or 5, then I have 3 options here. There's 3 numbers that could go here. But now how many options do I have for the last number? Almost. 3, yeah, because I can now put the 7 back in, right? So there's 4 odd numbers altogether. I can only start with 3 of them, but I can end with any of them, right? So I now have 3 odd digits left. So I've got the 2 left over and 7. I put 7 back in there. Right? So let's say, for example, this first digit is a 5, right? There's now 3 possibilities for the last one, 1, 3, or 7. Okay? Now that I take care of those 2 restrictions, again, there's 5 left. So these are still 5 times 4. But yeah, like if you have restrictions in 2 places where there's overlap in the pool of objects that you can use for those places, you have to divide it into cases. Right? It's tricky. So this would be what? 20 times 9, this is 180. We have to add them together. Plus 8 times 9 is, no. Sorry, 8 times 20, 160. So there's 340 possible numbers that you could make with those specific restrictions. Okay? That's a tough question because, and you can see how, It's a very short question. Like if you look at the number of words in that question, but then the amount of nuance that's built in, it's a lot of nuance that you kind of have to pick apart from just that very short description. Yeah. But what I would do is look out for this kind of thing, right? Where do the restrictions lie? Look at the pool of values that you have, and you can see that there is overlap. Right? When there's overlap in those, in what you can use in the particular places that the restrictions go, you often have to divide it into cases. Okay, any questions? All right.